This talk is based on a presentation given at Ausrail in November 2025. Rail emits only about 1% of Australia's CO2 equivalent emissions, while the rest of the transport industry emits 21%. So you might expect it would get a free pass. It doesn't. Rail operators with large diesel fleets are identified as big polluters under the Climate Safeguard Scheme and must reduce emissions by 4.9% per year. There is currently no technology available to do this, so they are forced to buy carbon credits instead. Outside our major cities, rail is powered by diesel, and there are around 2,200 locomotives and 250 diesel multiple units in operation. Diesels have long lives, and were it not for environmental legislation, most of the current fleet would still be in operation in 2050. So how can operators become net zero and still stay in business? We could electrify everything. Australia has around 41,000 kilometres of track, of which around 3,400 kilometres are electrified. To electrify the remainder might cost around $190 billion at $5 million per kilometre. Batteries and hydrogen have been proposed as cheaper ways to electrify. Currently, the operating range of battery-operated trains is limited to around 200 kilometres without charging, which is not enough for most routes. Batteries may be the solution for ore trains in the Pilbara, where the mines are around this distance from the port, and being predominantly downhill in the loaded direction, regenerative braking can supply a lot of the energy. Even so, the first prototype bells have only just been delivered to Port Hedland, and it will be some time before they are hauling iron ore. Even if batteries were the solution, to get to net zero by 2050 would require replacing or converting 100 locos per year at a cost of perhaps $5 million each, or $12.5 billion in total. But for now, batteries are only suitable for shorter distances. Is hydrogen the solution for the longer routes? Fuel cell-powered trains have been in service in Germany since 2019, with several small fleets of Alstom I-Lents on regional services. Pictured is a refuelling station for a fleet of 12 two-car sets. The hydrogen is brought in by truck from a chemical plant 35 kilometres away and stored at 50 megapascals. This is a very expensive process. Renewable hydrogen is even more costly and has a cycle efficiency of only around 25%. There has been no progress since 2019. Fuel cell cars are dead in the water. Toyota started developing the Mirai and Hyundai the Nexo more than a decade ago, when nobody thought batteries could ever have enough range to replace petrol. But now EVs can match fuel cell range, but at less than half the price. These are nice cars, but a market failure. Therefore, there is no reason to build a hydrogen fuel network. Some manufacturers think fuel cell trucks are not dead yet and are still developing them. If they were to succeed, it would be necessary to develop the fuel network to supply them, and rail could piggyback off this network. But it is chicken and egg. Without demand, no one will develop the network, and the price will remain exorbitant. If only we could keep using our diesel fleet. What we really want is a drop-in zero-emission replacement fuel which would require no modifications to existing locos. Vegetable oils do not burn cleanly and will rapidly coke up a diesel engine, but can be converted to biodiesel, or fatty acid methyl esters, which have been around for decades. It is easy to make fame by heating vegetable oil with methanol, which breaks the triglyceride molecule into 3 chains. This can be done in a pot on a kitchen stove. These methyl ester molecules are very similar to diesel, but have 2 oxygen atoms near the end of the chain, as in the diagram. Oil and water don't mix, but these oxygen atoms make esters hygroscopic, and they will hold water in suspension, which is bad for engines. Moisture promotes the growth of microbes and sludge if biodiesel is stored for any period of time. Therefore, most engine manufacturers will only allow blends of 5 to 20%, and pure biodiesel is rarely used. HVO, or hydrotreated vegetable oil, overcomes this problem by removing these oxygen atoms and replacing them with hydrogen to produce hydrocarbon molecules exactly like diesel. This requires using heat and high pressure in an industrial process which is much more costly than making biodiesel. However, both biodiesel and HVO have a problem. They are always promoted as having been made from waste cooking oil, but we don't eat enough fried food to generate enough waste oil. There have been a number of scandals in Europe where virgin palm oil, labelled as waste, was imported from Asia. In Australia, rail consumes around 1,700 million litres of diesel annually, and it would require about 4.5 million tonnes of grain to make this much oil. The 2025 canola harvest in Australia was about 6.5 million tonnes, or about 10% of all grain production. While sufficient for rail, road and aviation would also be competing, requiring 20 times as much, or more than Australia's total grain production. There is no possibility that fuel could displace food production. This is truly a dead end. It is even questionable whether oil from grain is truly zero emission, since nitrate fertilisers require ammonia, which is currently made with hydrogen from natural gas. But what about synthetic fuel from biomass? Any hydrocarbon can be made using the Fischer-Tropsch process, which was invented in the 1920s and allowed Germany to make liquid fuels from coal during World War II. So did South Africa when it was under sanctions during the apartheid era. Like HVO, the molecules are the same as in fossil diesel fuel. There have been several gas-to-liquid projects in the USA using natural gas or methane rather than coal, as is pictured here. To make a net zero fuel, biomass could be used, or even CO2 extracted from the air. But this is more expensive than HVO and at least 3 times the cost of regular diesel. Fuel is typically a third of the operating cost for freight operators, so a 3 times cost increase would be an almost impossible burden. Having exhausted the drop-in options, are non-drop-in alternatives cheaper? This table lists most of the alternative fuels which could be made from renewable resources. Except for methane, they all have significantly less specific energy than diesel. DME is the only one which will work in a compression ignition engine without a pilot fuel. A pilot fuel requires 2 sets of fuel systems on the loco. Some are also gases at ambient temperature, which means they must either be highly compressed or liquefied to store the quantity needed on a locomotive. The first, ammonia, is the only true zero carbon fuel, being a compound of nitrogen and hydrogen. However, ammonia is currently made from natural gas using the Haber-Bosch process, resulting in 2.6 kilograms of CO2 for every 1 kilogram of ammonia produced, about the same as burning a litre of diesel. Green ammonia uses hydrogen produced by electrolysis, which currently costs a great deal more than when made from natural gas. Nevertheless, there is great interest in ammonia as a zero-emission fuel for shipping, and several manufacturers have produced engines capable of running on ammonia. But there are several disadvantages. Ammonia is a gas at ambient temperature. However, it can be liquefied at minus 33 degrees C, a temperature within the range of conventional refrigeration. Ammonia has poor auto-ignitability and slow flame speed. It generally needs diesel as a pilot fuel, and not just a little. In a converted engine, you may achieve 60% substitution of diesel, although this can be higher with specially designed combustion chambers. It therefore requires a dual fuel system, with modifications to the engine. High compression improves combustion, but also gives high NOx, and so exhaust aftertreatment is required, adding to the complexity of conversion. Low compression will lead to unburnt ammonia in the exhaust, which is toxic, and the energy is less than diesel, 44% by mass and 37% by volume. And it needs to be stored in a pressure vessel rather than a tank, so range with onboard storage will be less. For longer routes, an external tanker would be necessary. Tankers designed for LPG can be used for ammonia, and one like this would be adequate to provide fuel for 2 locos on a train running from Melbourne to Brisbane. Methane, or natural gas, is included here because it is considered as a transition fuel. There was a great deal of interest in natural gas in the USA when the fracking boom started, as in terms of energy, the price was about 20% of diesel. Both EMD and GE did significant development work, and there were trials with several Class 1 railroads. However, there are significant operational difficulties, and in the end, only Florida East Coast and one Mexican railroad adopted it for regular operations. Being a gas, methane must be either highly compressed or liquefied for storage. The liquid temperature is minus 162 degrees C, which requires a double-walled cryogenic storage vessel. Florida East Coast developed a special crash-resistant tanker wagon, as there are significant concerns about side impacts at level crossings. The wagon sits between 2 locos, and there are hoses between the vehicles transferring water from the locomotive radiators to heat exchangers on the wagons, where the LNG is vaporised and then transferred through hoses to the locos. Diesel is still required as a pilot fuel to ignite the methane, but around 80% substitution is achieved. Natural gas is a fossil fuel, and CO2 is only reduced by about 28% relative to diesel. Methane could be produced from biomass, but this is probably not the easiest or cheapest path to net zero. Which brings us to DME, or dimethyl ether, which can easily be made by joining 2 molecules of methanol. Its key advantage is that of all the alternative fuels listed on the earlier slide, it is the only one which will ignite in a compression ignition engine. Its cetane number is even higher than diesel. Other advantages are that it produces less NOx and almost no particulates or soot. Because of this, there was some interest in DME as a clean fuel for urban buses about 2 decades ago, before all the focus turned to CO2 emissions. However, it does have some disadvantages. The chief is that as a gas, with boiling point at minus 25 degrees C. In this respect, it is similar to LPG or propane. However, it remains liquid at 20 degrees with a pressure of 500 kilopascals, which is a pressure we are used to working with on rail for air brakes. It requires conventional pressure equipment, unlike methane or hydrogen. It is like barbecue fuel versus rocket fuel. Pressures of 35 to 70 megapascals are used for hydrogen, or it is liquid at 20 degrees above absolute zero. However, another problem is its low viscosity, less than 10% of diesel. Pumps and injectors wear out faster, and therefore it needs an added lubricant or different injectors. Energy is lower than diesel, 28.9 versus 42 megajoules per kilogram. Fuel tanks need to be cylinders, not a rectangular box as on this loco. Cylinders fitted in the space of a 10,000 litre diesel fuel tank would hold the equivalent energy of 4,650 litres. While this would be sufficient for intrastate work, a tanker would be needed for longer journeys. DME is generally made from methanol, which can be made from wood or other biomass. Heating wood gives synthesis gas, a mixture of carbon monoxide, hydrogen, CO2 and some methane. As produced, syngas generally has 50% more carbon monoxide than hydrogen, but to make methanol requires a 2-to-1 ratio of hydrogen to carbon monoxide. The water shift gas reaction is used to boost the proportion of hydrogen by injecting high-pressure steam into the mix. However, this converts carbon monoxide into CO2. This step could be avoided by using green hydrogen produced by electrolysis, reducing the amount of CO2 and the amount of biomass required. However, it is currently more expensive than water shift. To produce DME equivalent to rail's annual 1,700 million litre diesel consumption would require 10 million tonnes of biomass, assuming methanol produced with water shift. Australia exported 12.3 million tonnes of wood chips in 2022, but gas from cane is around 5 million tonnes, so the quantity needed is not outlandish. However, rail may be competing with aviation and road transport. They would require 20 to 40 times more biomass than rail if they go down the Fischer-Tropsch synthetic fuel path. Which raises an important question. Is fuel from biomass really net zero? CO2 is released when you burn DME or any synthetic fuel or wood, and the process of making methanol also releases a lot of CO2. But to put this into perspective, it is estimated 830 million tonnes of CO2 was released by the bushfires of 2019-2020. However, because of regrowth, the CO2 released from burning wood is not counted. Australia's official CO2 for 2019-20 was only 528 million tonnes. Some might argue that rather than wait for the bush to catch fire, causing massive destruction and killing millions of marsupials in the process, we could selectively harvest our native forests. But I won't even mention that. Nevertheless, the argument stands that if there is regrowth, burning methanol made from wood or any other biomass is net zero. Methanol itself can be used in a diesel engine with a pilot fuel, and is also the subject of a lot of R&D for ship engines because it is easier to use than ammonia. It would still be net zero if the pilot fuel is HVO or synthetic diesel, or even DME. This might be an economical combination, with methanol as the bulk fuel and the more expensive pilot fuel in smaller quantities. Being a liquid, methanol is easier to store and transport than DME as a pressure vessel is not required. There may even be an argument for making DME at the point of use, from methanol made near the source of biomass. While its energy by volume is 82% of DME, methanol comes out slightly better even for onboard storage, as it can use a rectangular tank versus cylinders. Therefore, a 10,000 litre tank of methanol has energy equivalent to 4,900 litres of diesel, giving about half the range, and again would need an external tank for longer routes. Assuming batteries and electrification replace half the fleet, for the remainder we would need 1.3 million tonnes a year of methanol. Australia had a methanol plant in Laverton, but it closed in 2016 due to the rising price of natural gas. However, Able Energy is proposing to build a 300,000 tonne a year green methanol plant in Bell Bay, Tasmania, to supply fuel for shipping made from biomass and green hydrogen. We would need 4 such plants to supply the rail industry's needs. 5 million tonnes a year of biomass would be needed to run half the diesel fleet on DME. This equates to around 15,000 tonnes per day, or about 4 trainloads of biomass. In conclusion, it would be possible to make diesels net zero with DME. The pros for DME or methanol are: it is net zero, carbon neutral if made from biomass. It could use existing locos with some modifications to injectors, pumps and tanks. It is much easier to store and transport and handle than liquid or compressed hydrogen. And it is cheaper than hydrogen or synthetic diesel, but nevertheless will cost more than diesel. Is it a viable path for the Australian industry? Rail demand is sufficient for an independent DME ecosystem, irrespective of what other modes of transport do, which is not the case for hydrogen. This ecosystem requires methanol production, sources of biomass, and rail links to the production facilities. If we choose this path, it could be up and running by the early 2030s and carry us through to the mid-2040s when maybe other technology will be available. This could be a concrete plan to present to government as an alternative to buying carbon credits, and it could have export potential if other countries follow our lead. So, don't send your diesel to the scrapyard just yet.